I'd like to welcome you to today's presentation on ultra-high pressure, and we're going to talk today about both the extinguishing and penetrating capabilities. Now, there are a number of corporations on the market offering ultra-high pressure for extinguishing. However, Pyrolance not only offers those systems, we have a unique proprietary technology which allows us to do piercing capability as well. Let's talk about extinguishing theory on ultra-high pressure. There currently are no real definitions for what normal pressure is, high pressure, or ultra-high pressure. But for our purposes, we like to consider normal pressure as being 500 psi or 35 bar or less. From the 35 bar to 70 bar or 500 to 1000 psi, we consider that high pressure. And then beyond 1000 psi or 70 bar, we consider that ultra-high pressure. Now, with regard to what ultra-high pressure is and what it is not, it's important to understand a couple of concepts. First of all, ultra-high pressure is a very viable tool to put in your toolbox. It does not, however, replace normal pressure. It does not replace foam. It does not replace compressed air foam. It's a tool to be used in addition to those other tools that you have. Second of all, ultra-high pressure is a validated and proven technology. There have been a number of studies done which have proven this in recent years, as well as in European and other international markets. First of all, the Air Force Research Laboratory at Tyndall Air Force Base did a very extensive study in 2006 to 2008. We'll touch on those results later on in this presentation. The National Research Council of Canada, as well as some testing that was done in Oklahoma City that we were involved in, and we'll share those results with you as well. Thirdly, UHP is safe. We operate in most of our configurations at 1500 psi, 100 bar or less. By comparison, when you go to the car wash to wash your car, your truck, your boat, you're operating at sometimes even twice that pressure. Now, with our lance, it does have the potential to injure or even kill a person. So therefore, when you carry, you must always remember that you must maintain muzzle discipline and keep your finger off the trigger, except when you're going to make a cut. We purposely designed the unit to look like a weapon so that it serves as a constant reminder to maintain that muzzle and trigger discipline at all times. And lastly, for those of you that are approaching my age and getting a little bit long in tooth, today's UHP is not yesterday's John Bean system. The John Bean system, if you remember that or have heard about it, operates in that normal pressure range of about 500 to 700 psi. Concept is very similar, but today's UHP is much different, much more efficient than yesterday's John Bean system. Now, it's important to understand what ultra-high pressure does compared to normal pressure. When you look at the diameter of the droplet size, and typically we measure these in microns. You don't have to remember that, but just for order of magnitude, it's important to know the size or the difference in the size of those water droplets that are coming out the two different types of technologies. With normal pressure, droplet size is typically in that 900 to 1000 micron diameter. Whereas with ultra-high pressure, we're typically down in that 90 to 100, maybe even 150 microns. Much, much smaller than normal pressure. So what does that mean to you? Well, think of it this way. If we had 2 glasses of water, and we had 2 ice cubes that we were trying to cool those 2 glasses of ice, both of those cubes of ice have the same mass and the same cooling potential. If I put 1 ice cube into 1 glass, but before I put the second one in the second glass, I broke it up into small chips. The difference is that the one with the smaller chips would cool much faster. Again, the same mass, the same cooling potential, but why would it cool much faster? The reason being the greater surface area. Well, that's the same thing that happens with ultra-high pressure. When we pressurize that droplet of water, it breaks it up into small pieces. Those small pieces, or those small droplets, okay, have a greater surface area. They greatly improve the efficiency of that micro droplet to absorb heat, convert to steam, and cool. Just like that single ice cube. That single droplet of water is not very efficient in terms of absorbing heat and cooling. So think of that droplet of water going into the fire. Only about the outer 10% of that droplet of water absorbs the heat, converts to steam, and cools. Okay? Whereas when we do the same thing as breaking up that ice cube into small pieces, that pressure will break up that droplet of water into many, many tiny droplets. And so now, with that greater surface area, that water is so much more efficient. In fact, it's 90% efficient. And that's what enables us to, number one, cool faster, and then second of all, cause less water damage to the structure, or for that matter, consume water when we're trying to extinguish and cool. Now that pretty much gives you a quick overview of the theory of ultra-high pressure. Let's take a look at some of the empirical evidence and some of the studies that have been done recently to prove ultra-high pressure and its efficacy. The first that comes to mind is the Air Force Research Laboratory testing that was done between 2006 and 2008. Their whole premise was to find a replacement vehicle and platform for the P-19 aircraft rescue firefighting vehicle. It's a great vehicle. It's a great firefighting tool. The problem is only one of those units will fit into the belly of a C-130. And to do so, they have to remove the roof turret and drop the air pressure in the tires to fit it through the back door. Now what they were looking for was a vehicle that would have the same firefighting capability, the same knockdown potential as their beloved and proven P-19, but be able to fit two of those vehicles into the belly of a C-130. Now, what that required is something or a technology that would outperform normal pressure water and foam. Now, as they looked at different technologies to do that, what they came across was the ultra-high pressure. So they realized that there was tremendous potential in exploring this technology further. And as they started doing the testing, they realized that they really had something in doing this. So what they did was they fitted out two P-19s, one with the normal pressure, 700 gallon per minute nozzle capacity, and a second P-19 as a test platform that was fitted with a 300 gallon per minute ultra high pressure pump platform on it. I'm going to show you a side-by-side video, and they did over 100 of these side-by-side tests with ultra high pressure compared to normal pressure. The video I'm showing you is a side-by-side comparison. On the left you'll see the P-19 ultra high pressure crash truck with going up against, on the right, the normal pressure P-19 vehicle. And you'll notice that on similar fires, the P-19 extinguished the fire in about 31 seconds, compared to the P-19 that was normal pressure, about 43 seconds. The water consumed for the ultra-high pressure was 151 gallons, compared to 525 for the normal pressure vehicle. Now you'll also notice that on the P-19 ultra-high pressure vehicle, they were using 6% Class B foam, compared to only 3% on the normal pressure vehicle. There's a reason for that. And you'll say, well, you know, that they're using a lot more foam, and so it's not a fair comparison. The 6% was not required for the extinguishing. The 6% was required to have enough product on the surface of that pit fire in order to pass the burn back test. And if you look at the amount of foam concentrate that was consumed in those two comparative tests, at 151 gallons total with the ultra high pressure and 6%, that represents just over 9 gallons of foam concentrate that was consumed. Whereas with the 525 gallons at 3%, that represents about 15 gallons of concentrate that was used. So even at twice the proportioning rate, we still used only about 60% of the foam concentrate with ultra high pressure. So what did the Air Force Research Laboratory results suggest? I happened to be involved in that test with another company that I was working with at that time. Only I was involved on the foam proportioning side. Pyrolance was involved in that test from the ultra high pressure mist side. And what I remember is we started out those tests at about 4,500 PSI. The Air Force Research Laboratory began dropping the pressure down in stages to understand where the optimal pressure range was for ultra high pressure. I believe they came down to about 1,000 or 1,100 psi, but the sweet spot where the optimal droplet size and the best extinguishing and cooling results were was right around 1,500 psi. What they found was that gave the optimum droplet size of about 90 to 100 microns, and it gave the optimum droplet velocity at about 125 to 150 meters per second. And what that resulted in, on average, was about 1/3 the application rate of normal pressure. The conclusions that they came to was that, number one, ultra-high pressure gave a much faster knockdown compared to normal pressure. They consumed far less water. They had improved efficiency, not only with the equipment, but also with the firefighting personnel. And they were able to get by with a lot less in water additives. In other words, the amount of foam concentrate that was consumed. In addition to that, with pyrolamps being involved in their piercing or penetrating technology, even though it was not part of the test, they soon realized that there was a tremendous additional potential by having the penetrating capability in terms of being able to penetrate composites, armor, the speed that they were able to access the seat of the fire, and lastly, the reduced amount of damage to the aircraft as a result of penetrating with ultra-high pressure water compared to using a mechanical. Now, the Air Force Research Laboratory testing was not limited to Class B or fuel fires. They also did some testing on wildland and structural fires, as have a number of other agencies. And what you'll see in this slide is that compared to normal or low pressure, the amount of water consumed with ultra-high pressure technology is significantly less than with normal pressure. So what does that really mean? In other words, how can a small 10 or 20 gallon per minute water stream of ultra-high pressure equal or outperform that of a 100 gallon normal pressure stream? Well, let's take a look at the graph. On your left, you'll see the total gallons flowed of a normal stream and an ultra-high pressure stream over time. In this case, we're comparing a 100 gallon per minute normal pressure stream to a 20 gallon per minute ultra-high pressure stream. And on the bottom axis, on the x-axis, on the bottom of that slide, or that chart, you will see time, and in this case, we're going out to 60 minutes. Over 60 minutes, that's 100 gallon per minute normal pressure water stream will flow about 6,000 gallons of water, compared to the ultra-high pressure stream flowing at 20 gallons per minute, which over 60 minutes will flow a total of 1,200 gallons of water. Now on the right-hand side, let's factor in the efficiency of those two water streams. Remember, we said that normal pressure is only about 10% effective, whereas ultra-high pressure is 90% effective. So if we look at the efficiency, in other words, the total amount of water that's really absorbing heat and converting to steam of those two water streams that we see on the left, what we see with the ultra-high pressure is that at 90%, there's about 1,080 gallons after a 60-minute period that is absorbing the heat and converting to steam and cooling. Whereas with the normal pressure at only 10% efficiency, we're only getting about 600 gallons that are converting to steam and cooling. So you can see how a much smaller ultra-high pressure stream can be as effective or more effective than a normal pressure stream in cooling and absorbing heat. So what does that really say to us in terms of the benefits of ultra-high pressure as a result of these tests that the Air Force Research Laboratories and others have proven? First of all is firefighter safety. Number one, with ultra-high pressure, we get a very effective water stream, reach of 60 to 85 feet. Second of all, we get that immediate knockdown. Third, we get the hydraulic ventilation that takes place. From an environmental point of view, we have much better use of water in water efficiency. We get less runoff, we get less water damage. From a firefighter fatigue point of view, by using smaller handling, 3/4 inch, as opposed to say 1 3/4, 2.5 inch hose lines, we greatly reduce the amount of fatigue on the firefighter. And getting our crews back in service is much faster. This has benefit both for the municipal department as well as the volunteer departments. First of all, in the municipal department, you typically are running 15, 18 calls per shift. So that means that you're back in service faster, that you're on to your next call. For volunteer departments, Typically, we're taking people away from their jobs or from their families to go fight a fire. By getting them back in service quicker, they're able to spend more time at their jobs, being productive, or with their families. And lastly, what we found is that with the ultra-high pressure, we are able to configure systems and models to easily fit the application or the vehicles that we're working with or the constraints of the vehicles that we have. For example, the Air Force unit, they're able to go with much smaller vehicles or a smaller platform. Many of the municipal vehicles today are required to do multiple tasks compared to, say, 15, 20 years ago. And so we're able to outfit those with a smaller pump, with a smaller power plant on it. We're able to incorporate more functions into that vehicle, such as medical and hazardous materials, trench rescue, or what have you. So we're able to customize that vehicle and make it more efficient for less money. Let's also consider why ultra-high pressure works so well. One of the factors to consider is the 30% number. For example, if we're fighting a structure or a wildland fire, we know that if we can get the moisture content of that fuel up to 30%, it's not going to burn. Similarly, if we can get the moisture content of the humidity in an environment up to 30%, combustion will cease. And so with those smaller droplets, with that longer hang time, we're able to get that mist to saturate the environment and raise the humidity up to and exceeding that 30% range. And now we can stop combustion in its tracks. Now let's take a look at some of the extinguishing applications for ultra-high pressure. Typically, the delivery types are very traditional types of nozzles, ones that may look exactly like the combination nozzles we see under normal pressure. But one thing I would caution you is do not take a normal pressure nozzle and adapt the fitting to fit a 3/4 inch hose or a 1/2 inch hose and hook it up to an ultra-high pressure system. The reason being is that these nozzles that are rated for ultra-high pressure have been designed and tested to accommodate the pressures that we're going to see in ultra-high pressure, whereas a normal pressure combination nozzle was not designed nor tested that way. You'll cause severe damage to the nozzle by exposing it to ultra-high pressure, and second of all, you may cause injury to yourself or another firefighter. The other type of nozzle is typically what's referred to as a wand nozzle, similar to what we see in a car wash or a pressure washer. And this is in the illustration that we have on this slide. This nozzle is also fitted with a foam tube at the end of the nozzle. That foam tube is an aspirating tube with air holes at the rear of that tube, and we can slide that tube forward or rearward toward the rear to enable us to change the amount of air that is being aspirated into that stream. And that will change from, say, wet foam to dry foam. And the other thing that you'll notice is that on that foregrip, that will pivot forward and backward, and that changes from a straight stream to a wider fog pattern. So very similar to a car wash nozzle, but with a few extra enhancements on it, and it works very well in ultra-high pressure firefighting applications. When we look at end-use applications for ultra-high pressure, the applications are virtually limited only by our imagination. Military applications, we have both Air Force, Army, Naval, Coast Guard, the marine environment, whether it be a municipal marina, whether it be a cruise ship, cargo container ship, or petrochemical transporter, both municipal and volunteer fire departments, we can find numerous applications for ultra-high pressure. Forestry services, again, wildland applications, the urban interface, aviation, whether it be a municipal airport, whether it be an Air Force, law enforcement, could be for SWAT applications, counterterrorism, industrial, this can be oil and gas industry, it can be for mining, it can be for chemical processing or warehousing applications. All of these have tremendous applications and numerous applications for ultra-high pressure. Now let's take a look at the penetrating capabilities, and as I said at the outset of this presentation, that the penetrating capabilities of ultra-high pressure technology is something that's unique to PyroLanes. We like to say, meet the hand line that pierces through walls, floors, ceilings, steel, concrete, wood, any type of building material, aircraft, bulkheads on ships, what have you. And we affectionately refer to ourselves as the hole in the ball game, as you'll see in a moment. We, with our technology, what we do is we take ultra-high pressure and we inject an aggregate into that water stream and couple that with the proprietary nozzle technology that we have. And we're able to penetrate virtually any type of barrier that you may encounter. Now, when we conducted tests with the military, they gave us a composite material, and we went through that virtually instantly, even without the use of the aggregate, just with the ultra-high pressure. Then they gave us quarter-inch steel, and we went through that. Bear in mind, these tests were done at about 4,500 PSI. Most of our technology for municipal applications and today are done at about 1,500 PSI. But we do do a number of applications or models that are unique for unique applications, such as bomb disposal, or in areas where very thick concrete, particularly reinforced concrete barriers are encountered, and we do those up around the 4,500 PSI. So depending on your needs, we can accommodate whatever type of barrier that you may have in your applications. They also asked us to go through 3/4-inch aluminum, and we went through that. The reason why they chose those three materials is they were developing an armor package that consisted of those three materials, a sandwich of that, a space, another sandwich of those three materials, a space, and a third sandwich. And we went through all of those. What I'm going to show you now is going through the composite as well as the quarter-inch hard steel in the video. Now, what you'll also notice is that as we're flowing that ultra-high pressure lance into the air, notice the hang time of those ultra-high pressure droplets, those micro droplets. And there you see he went through the composite, and again, virtually instantly in doing that. Now what we're going to do is demonstrate for you going through the quarter-inch hard steel. You can see that he's starting to make penetration there. It's coming through the back side, and now he's penetrated through that quarter-inch hard steel. And if this were a barrier and a fire were on the other side, what we would be doing is turning off the aggregate and continuing to flow that ultra-high pressure mist into the seat of that fire and cooling that thermal layer. Then after we went through the composite, the steel, the aluminum, they gave us another test to do, and that was with bullet-resistant glass. Bullet-resistant glass typically is in about the half-inch thickness range, but they made it a little more challenging for us. They gave us 7 layers of that bullet-resistant glass sandwiched together. And I'm just going to show you the last few moments of that penetration, and you can see going through that 7 layers of bullet-resistant glass. This was a very windy day, and again you can see those micro droplets still hanging in the air and saturating that environment. If this were a compartment that we were penetrating into, those micro droplets would be saturating that environment, raising that humidity up to that 30% or more, not only cooling and penetrating that thermal barrier, but also creating an environment that the humidity would not support combustion. There you see that we've penetrated through, and now what they would do is typically in a firefighting application, turn off that aggregate, allow the mist to continue to flow into that environment and penetrate and cool that thermal layer. With our 1500 PSI models, you can see some of the common construction materials that we may encounter. For example, a double break faced wall, 3/4-inch plywood, concrete block in the lengthwise configuration, 1/4-inch aluminum, a FedEx cargo plane, for example. All of these typically are under 30 seconds or less in terms of penetration time. So the benefit of ultra-high pressure, when you couple that with the piercing capability that Pyrolance offers, is that now what we can do is position the firefighter safely outside of the structure or the barrier. In other words, the firefighter no longer has to make an aggressive interior attack to get to the seat of the fire. What we can do is make an offensive, aggressive interior attack from a safe defensive exterior position. And by doing that, we penetrate through that structure, whether it be a container, whether it be a building, whether it be an aircraft, whether it be the bulkhead on a ship, whatever that may be. We can penetrate that from the safety of the outside. We now can attack that heat, that thermal layer, and cool that environment down. And once it's cooled down, we can make a safe interior attack. What that means is we don't expose the firefighter, first of all, to the heat, to the risk of a flashover, to the risk of a collapse or going through the floor into a lower level. We enable that firefighter or that smaller size crew, if you're short-handed, can't do the 2 in and 2 out, you can make that interior attack, you can hold that fire and even knock it down from the safety of the outside of the structure until other crews arrive. So tragically, we've seen all how firefighters such as this on the left, venting a roof or an attic, would ultimately turn into something that you see on the right. I don't mean to sensationalize this, but unfortunately it's the reality of our industry. It's the reality of what we do all too often. And now what we're able to do with the PyroLance ultra-high pressure piercing technology is from the safety of a bucket, from the safety of a ladder, or even from the ground, we're able to penetrate and knock down and extinguish that fire on the inside of an attic or in the inside of a structure without the risk of a collapse, without being exposed to the heat, without even injecting oxygen into the seat of that fire. Let's take a look at another test that was done. This was the Oklahoma City sequence, and this was done in a second-story apartment in the back bedroom. The fire was set there. This was a test burn, not an actual fire. The beginning temperature was approaching 1400 degrees Fahrenheit or about 750 degrees centigrade. The lance line was pulled, and rather than making a traditional entry up the second floor, knocking down the door, going down the hallway, what was done was the crews went in on the first floor of the apartment building, below the apartment where the fire was. And they penetrated the ceiling, and what you're going to see is the ceiling was a foam tile ceiling. They cut a hole in that, and then they penetrated about a 6-inch hollow concrete ceiling, and then injected the mist into the second-story apartment. Where they came through in that second-story apartment was not in the back bedroom where the fire was, but down the hallway at the entrance to that apartment. Within about a minute and a half of starting that flow, that temperature dropped to almost 200 degrees or about 100 degrees centigrade. So let's take a look at what that sequence looks like, and I'll describe what's going on. On the left-hand shot, you'll see the firefighter going in, and he's cutting the hole in the foam ceiling tile, and now he's penetrating through to the hollow concrete. He's already through the concrete, and immediately you can see the impact down the hallway and around the corner into the bedroom. That drawing at the lower right-hand portion of the screen, the window in that bedroom is what you're viewing just above that, and already they're getting good steam conversion in that, and the cooling is taking place. You're seeing the knockdown take place, and that temperature just dropping down rapidly into that second-story apartment. With that temperature drop down, now it's safe for crews to make a traditional entry through that apartment door, and on the second floor, go into the overhaul of that fire and get that fire knocked down. But they are no longer exposed to the heat. They're no longer exposed to the risk of a flashover. They're no longer exposed to the potential risk of either a roof collapse or going through the floor to the lower level, and they are not injecting oxygen into that fire to feed it. So what are some of the findings from the Oklahoma City sequence? First of all and foremost is improved firefighter safety. We're able to make that an indirect attack from an exterior position without having to expose the firefighters to the heat, the risk of a flashover, the stress of carrying up a 2.5 or 3-inch and 3/4 hand line. We've got much lighter hose with that 3/4 inch ultra-high pressure line. We make non-sparking penetration. In the event that we had something that was explosive on the other side, we would not be setting that off with the penetrating techniques that we use with ultra-high pressure. We get much faster cooling. We drop the temperature of that environment much quicker than we would with a traditional hand line. We use far less water. We get that fire knocked down quicker. There's less water damage, there's less smoke damage, and less fire damage. And what that means is that we have quicker, improved visibility. We use far less water additives, and we preserve evidence for arson investigation. So let's now take a look at some of the components that are used in the ultra-high pressure piercing technology. Obviously, we have our traditional water tank. We have an ultra-high pressure pump that can be powered by a gas, a diesel, or a PTO type hydraulic system. We have an abrasive tank. We have a hose reel. And then we have a control panel and a nozzle that are very unique to PyroLance. And that is, we utilize wireless technology to trigger our valve, open and close our valves, and throttle up and down our power source. Now, why do we do the wireless technology? Well, first of all, if we were to use a traditional type nozzle with a ball valve in it, the first time that we flowed the aggregate through that nozzle, we would destroy that valve, destroy the seats of that valve, and it would be leaking. So what we do instead is the controls that we have on that PyroLance piercing nozzle are electronic switches that we use on that trigger and on the abrasive control. And we send that signal back to the base unit. On the left-hand screen, you see a compartment-mounted unit, and that is where the antenna is that receives that signal to turn on or off the water, turn on or off the aggregate. And our valves for the aggregate and the water are located downstream of the ultra-high pressure pump, upstream of that abrasive tank that you see in the diagram. So therefore, there is absolutely no aggregate going through those valves. And again, as I said, we're able to utilize this technology to flow the water, turn it on and off, flow the abrasive, turn it on and off, throttle up or down the engine or the PTO, the hydraulic drive, without doing any damage from the abrasive to those valves. The ultra-high pressure piercing lance, as I mentioned earlier, looks very much like a weapon. You'll see the adjustable stock on that to fit and accommodate any size firefighter. There's a folding antenna on the handle. But again, we want that look and feel when you're carrying and handling that lance, that you're thinking just like you're walking in the field hunting birds, that you need to maintain muzzle control and discipline. You need to maintain trigger and finger discipline as well. Notice from a safety perspective that we also have a water trigger safety lock, the red lever that folds down, which prevents inadvertent activation of the water trigger when you may be transporting or handling the lance. Ahead of the trigger, underneath the barrel, you'll notice a switch. That's our on and off switch for the aggregate. Push it up, and that activates the aggregate. Put it in the down position, that shuts it off. So to penetrate through a barrier, we would activate the aggregate. Once we're through and we want to continue flowing the ultra-high pressure fog or mist into that environment, we would just turn the aggregate off, continue holding the water trigger, and flowing that mist until we're sure that temperature is knocked down, the heat is absorbed, that the fire is suppressed, and then we go in and make the overhaul. On the fore end of the PyroLance is the foregrip, and that's adjustable for the position on that barrel. Can be moved out, can be moved in, depending on what's comfortable for the operator. It also serves as a tripod when combined with the trigger guard base, and that allows us to stand the unit when it's not in use. On the very tip of the lance, you'll notice that we have a three-pronged shield on that. On the tip, that enables us to position securely the lance to make one cut rather than moving it around. And then second of all, it allows us the proper standoff from the barrier so that a spray can be egressed out to the sides. And on the front end, you'll also notice that there's a deflection shield so that any spray that's coming back is deflected off to the sides rather than back at the operator. The tip is in there, and that can be changed simply by unscrewing that deflection shield, and that will gain access to the tip. It can be removed and then replaced with a new tip. These do not wear out very easily, but in the event that you should notice maybe more than 500 psi drop in operating pressure, it might be time to replace the aggregate tip. The module itself, whether it be a lance, a blitz, or a combination, relatively compact, and it's designed to be mounted in either a compartment, on a skid unit, or on a trailer. If it's in a compartment and it's a gas or or a diesel powered unit, they do come with a slide out tray, and that should be brought out so that heat can be vented properly and that engine can breathe. The unit that we're showing is a dual combination land splits module. The controls on that, you'll notice that we have a pressure gauge for both the pressure vessel as well as the pump pressure. We have a tach hour meter that will show you the RPM of the engine as well as the number of hours on the engine itself for service and maintenance follow-up. The manual controls on that pump panel allow us to manually override the lance and the water in the aggregate in the event that number one signal should be lost or that we desire to manually operate it at the panel. You also see the master power switch, an emergency stop, and the ignition switch on as well. Should point out that the control panel is illuminated for night operations. That make it much easier to see, as are the gauges. On the selector valve, in this particular model, we can choose between the lance reel or the blitz attack reel. And if you have a lance or a blitz only model, this selector valve would not be present on your model. In terms of typical configurations that we might incorporate ultra high pressure, we can see on the right a number of different types of vehicles. The uppermost is a wildland off-road type vehicle. This happens to be a Polaris chassis that was configured by ASAP 911. These are the only people that are authorized to stretch the Polaris chassis and still maintain factory warranty. This happens to be a unit that has a wildland package on it, as well as provisions for a toolbox, a Stokes basket, and an attendant. In the middle photo, we see a typical skid unit configuration with a water tank. This is a blitz-only application. And then in the bottom, we see a compartment installation. That could be on a new or existing vehicle. Could be a pumper, could be an ARF vehicle, could be a hazmat, could be a multi-purpose type rescue pumper. Again, many applications limited only by our imagination. Lastly, the configurations for Pyroland systems. You can get the piercing, the blitz, or a combination. These can be packaged for compartments, skid units, trailers, or even slingable units that could be brought in by helicopter. Power sources, gas, diesel, PTO, hydraulic, and any combination of those are available. If you have a need for a configuration that is not listed on this page, feel free to contact the Hole in the Wall gang at Pyrolands, and we'll be happy to accommodate you and discuss what options we can provide for you. That's it from Pyrolands and the Hole in the Wall gang. Hope you enjoyed the presentation. Hope you find it informative. And if you have any questions, please contact any of us, and we'll be more than happy to address your needs. Thank you.